Okay. So last time we talked about stress inside of the material. If the material is ideal, there's no flaw, no fracture, no cracks, and the stress should be just F divided by the cross-sectional area everywhere. So sigma should be the same everywhere inside of the material. But if we have any small cracks or flaws inside of a material, that would increase the stress. And we talk about this equation. EM, it's a maximum stress in a material when cracks are present. And those cracks and the flaws are sometimes called stress raisers because they can raise stress. Inside of this equation, we know this sigma m is going to be larger than sigma naught when we have cracks or flaws. A here is the length of the crack if that's a surface crack. So we have two different types of cracks. The one showing on this diagram here, it's a surface crack. So if that's a crack type, we're going to just use the length of that crack as the A for our equation. But we can have another type of crack, which is internal crack. If the total length of this internal crack is L, when we use this equation, that A equals half the L. So that's the difference. For A, when surface crack, just be the length of that crack. If it is internal crack, we're going to just take half the length. So notice the difference here. And rho T here, it's the curvature of that crack tip. So that's kind of that how sharp that crack is. The crack can have a very large rho or very small rho. So rho T controls how sharp that crack tip is. So once we know the geometry of the crack, types of the crack, we can use this equation to calculate what is the maximum stress in a material. And if there's no crack, the sigma m is going to equal to the sigma naught. But in most of the cases, this sigma m is going to be greater than the sigma naught. So that's one equation we learned to calculate maximum stress. And second equation we learned is to determine when a crack would propagate. Why is it important? Because a crack propagates, that will lead to fracture. Fracture means failure, right? As an engineer, we want to know when would the material fail. So another equation here to calculate what is the critical stress that would cause the crack propagation. So that's the equation, sigma c, that's a critical stress, equals to this equation 2 times E, that's Young's modulus of the material. This gamma S, it's a specific surface energy. And divided by pi times A, remember A is the length of the surface crack. It's half the length of the internal crack. And take the square root, that would tell us what is sigma c, which is a critical stress. So if your sigma m is greater than this value, sigma c, then you're going to have fracture. If your sigma m is smaller than sigma c, no fracture. So sigma c here is the limit point, the maximum stress you can have Once the stress is greater than that, you're going to crack. Everything's going to crack. You're going to have fracture. That leads to failure.
So today we're going to practice how to use those two equations. But before we start, any questions on those two equations we learned on Monday? Okay. Now let's look at a in-class practice problem. Check here, see what is going on. 1 over 2 minus.
Okay. Right, thanks for letting me know. Let me double check if my, okay, this one's good. Right, can you guys hear me on Zoom?
Yes. Perfect.
Students on Zoom, are you able to hear me?
Yes.
Good now. All right. Good. So we have example with a large plate of glass. This glass is subjected to a tensile stress. Oops, sorry. The tensile stress sigma naught equals 40 megapascal. And we're given gamma S, which is specific surface energy of that glass, equals 0.3 joule per meter square. And the Young's modulus of that glass is 696 gigapascal. And we want to find out if this glass will fracture when there are two small cracks are present. Okay, let me draw the cracks here. Okay, we have a couple cracks. The first crack, let's call this length L1. Another crack, it's inside of this glass. Let's call this length L2. And third crack, it's on the surface here. Let's call this length L3. And all cracks share the same curvature. The tip curvature, rho T1 equals rho T2 equals rho T3 equals 0.1 micrometers. L1 equals to 10 micrometer. L2 is 8 micrometer. L3 equals 0.4 micrometers. Sorry, let me check, yes. Okay. Okay, that's a setup of this example. We have a piece of glass with three cracks, small cracks. And we know the stress sigma naught applied to this glass. We want to find out if this glass gonna fracture under the given stress and the cracks. The three lengths, L1 it's 10 micrometer, L2 is 8 micrometer, L3 is the smallest one, it's 0.4 micrometer.